Welcome to the Foundation Lectures on NST. My name is Herwig Mannaert, and in this fourth part we discuss the expansion or code generation of software element structures and the harvesting and rejuvenation of these generated code bases. We have seen in the previous part that we need an advanced transformation where we have our functional entities, for instance data entities or task entities, not just transformed or implemented into a single class, data structure, data class, but that we have to encapsulate it in a very version transparent way, and that we have to surround this class with a number of peripheral classes interconnecting with tapping into various frameworks or solutions for cross-cutting concerns. And this collection of classes, which we use to implement a single functional entity, is called an element. In this case, a data element, more specifically an invoice element. Now, if we use this advanced transformation, we implement or transform every functional entity into a set of classes, data elements, task elements, and this allows us to cope with changes. This allows us to encapsulate changes and to avoid positive feedback due to change ripples. Because if we now apply a change on a functional entity, this may require multiple changes in the software implementations, but these changes will all be confined to encapsulated within the element, will not propagate further across the structure, and will not grow proportionally with the size of the system. Now, these normalized systems elements are structures around the implementation classes of the functional entities to interconnect with the various solutions dealing with the cross-cutting concerns, and we define 5 types of elements aligned very fundamentally with the basic software concepts: data element, task elements, flow connector, and trigger elements. And as we have said, it seems obvious to use code generation techniques to create instances of these recurrent structures, because they all have the same structure. Every functional entity needs to be implemented by a collection of classes interconnecting with the various cross-cutting concerns. And due to the simple and deterministic nature of these structures, we refer to this process as expansion and to the code generators as expanders. And we will come back to that later, but in a very simplified schematic way, we have, for instance, a number of settings representing the context, the technology, the various frameworks for cross-cutting concerns. We have a number of parameters describing an entity, like an invoice with certain attributes. We have the templates representing the structure of the various classes dealing with the cross-cutting concerns, and the combination of the technology settings of the cross-cutting concerns, the parameters of, for instance, the data entities, or more general, the functional entities. This combination with the template structures of the elements will lead to an actual instantiation of a number of classes, the actual implementation of an element. And for every single template class, we have therefore a template, and based on the technology settings, based on the parameters of the functional entities, every individual class is transformed into a real software class, but we will come back to that later. Now, what we need to consider in this point of time is the update of these recurring structures. The structure of all these elements should be recurring, because if we would have variations, this would only increase the complexity of the code base and decrease the consistency in the behavior. If you would deal in another way with persistency, access control, remote access frameworks for an invoice than for an order or a payment or a sensor or a customer, that would increase the complexity of your code base, would decrease the consistency of the behavior of your code base. So it is obvious that you should deal with these various cross-cutting concerns in a recurrent way across your functional entities. However, this recurring structure of classes dealing with, interconnecting with the various solutions of the cross-cutting concerns may need to vary over time. You may gain new insights, you may discover bugs or flaws in your structure, in your various classes interconnecting to the cross-cutting concerns, and you may want to apply different technologies, different implementations for the cross-cutting concerns. Now, these structural changes should be applied with retroactive effect, of course, because if you, having implemented 20 data elements, you see that you discovered a flaw or you need to adapt to a new implementation of cross-cutting concern, you need to do that not only for the new, but also for the 20 elements you already have implemented. Now, the funny thing is that the more frequent that you do these changes with retroactive effect, the more effort it means. So if you would have, for instance, 100 elements in your structure, and only after these 100 elements you decide to do a change in the recurring structure, that effort would be proportional to 100. But if you would do that every 50 elements, you would do that after 50 elements, and then after 100, and that would mean 150. If you would, for instance, do that every 20 elements, well, you would do that after 20 elements, after 40, after 60, after 80, and after 100, and so the total number of effort of recoding the recurring structure would be 300. And so it goes up. You can even derive a formula for it, which is quite a problem, because the longer you wait, the more outdated and possibly flawed your recurring structure is, and the more frequent you update your recurring structure, the more intense and the higher your effort goes. So you really are in a catch-22. If you wait for long times to update the recurring structure, it becomes outdated, probably flawed. If you do it too often, it creates a huge amount of work. So you need those recurrent stable structure to limit complexity, to guarantee consistency. You need to be able to adapt these recurrent structure of your elements to overcome flaws, technology changes. And you also need in every software system additional custom code, because you cannot 100% generate a software application. The code generators would become far too complex if you would be forced to generate every possible kind of software system people would want. So what you basically need is not just code generation or expansion, you need an automated mechanism where you provide code generation or expansion, but where you also provide a way to regenerate, to update or regenerate the recurring structure and to keep the custom code. Therefore, you need a way to harvest the custom code and to re-inject the custom code after the recurring structure has been regenerated. Now, remember we said this is a global overview of the concept of code generation, expansion based on software element structures. You have a number of functional entities like the invoice, the orders. For the data, you have a number of functional entities for tasks and actions. And then you have for the various types of elements, the template, the element structures, the element templates, the coding templates. And you basically instantiate these templates for every element you need. Now you have various dimensions or degrees of freedom. The first are the models. Suppose you consider the models. Basic models in software, which include data diagrams, entity relationship diagrams, data models, data entities. You would have flows, sequencing certain tasks in flows, and these are the most important models, and you would have definition of flows, etc. So if you look from the point of view of the models to the code base, well, what you would have is for every functional entity in the model, every data entity, every task, every flow, you would have an instantiation of that type of element. So for every data entity, you would have an instantiation of data element based on the name, the parameters, the attributes on that data entity. For every task, you would have an instantiation of a task element corresponding to the name of the task and the kind of argument. For every flow you define, you would have an instantiation of a flow element, and you would have instantiations of connector elements and trigger elements as well. So this is the view from the model, the functional entities, the functional models, to the code base. You have a second dimension, and that's you have the templates, the various templates of the types of elements. You have the templates for the set of collection of classes of the data element. You have templates for the set of collection of classes of the task element, the flow, the trigger, and the connector. And so from the point of view of the templates, the sets of template classes, you would have for every type of element an instantiation of this set of template classes for every instantiated element. So the data element set of template classes would be instantiated a number of times corresponding to the number of data entities. The task element set of template classes would be instantiated to task templates corresponding to the total number of task entities, and the same for flow element template classes, connector element template classes, and trigger element template classes. So this is the second point of view, the second dimension. You can look at the models, and for every entity of the model you have an instantiation of an element. You can look at the element templates, and for every type of element template you have an instantiation for the various functional entities. You can also look at the utilities, the cross-cutting concerns. There you have a number of frameworks you use, for instance, for persistency, transaction, for instance, for user interfaces, the model view model, framework, access control. And then you would have in the various elements, they would interconnect with, tap into these solutions. For instance, the persistency, of course, only the data elements would tap into the persistency solution or framework, and they would all have a class interconnecting to that framework. For instance, the transaction framework would be used, interconnected with, tapped into by both the task and flow elements, and they would have all a encapsulated class connecting to the transaction framework. For the model view model, of course, that would be rather interconnected with the various connector elements for the user interface. And the access control, one could imagine that both data elements, task elements, flow elements, and connector elements would all tap or interconnect into the access control framework. So this is a third viewpoint or dimension to this code base, where every instantiation of these elements would tap into a number of solutions or frameworks for cross-cutting concerns. A fourth dimensional viewpoint is the craftings, the custom code. As we have mentioned before, we do not believe it is possible to make code generators that can generate all kinds of software applications without the need for any custom code. So you would need additional custom code or craftings. And these custom code of craftings, they would consider of both injections within generated classes, within anchors of generated classes, and they would also consider of extensions, separate custom classes. And of course, these extensions or separate custom classes, they would be invoked often from within injections. Now, this custom code, we need to be able to separate them. Say, look, these are all these injected code snippets, these are all the extension classes, and that is another way of looking at it. These are the injections and the extensions that we can apply to a certain generated skeleton of recurring structure. And as mentioned before, we need to be able to update the recurring structure without losing the custom code. So therefore it is important to harvest those craftings or custom code from the code base. To harvest them and store them in repositories. And that would make it possible that if we would regenerate the skeleton, the recurring structure, with a new version, a second version of the element template classes, that we would, after regenerating that structure, we could re-inject the injections and the extensions, and we could once again use the created custom code in this better, new, and improved skeleton of recurring structure, dealing with certain flaws or new insights. And of course, we could do this on a continuous basis, because we could have discovered new flaws, improvements, etc. So we could have a third version of the templates for the various element types, and we could have a regeneration and recreation of the recurring structure, and we could have a re-injection of the harvested injections and extensions, and they would also diminish over time, because the better and more powerful the recurring structures become, the better and more powerful the skeletons become, the less need there is for extensive custom code. So we could re-inject it. Now, what we're basically saying is that it is very important to separate those dimensions of variability in this expansion process, because we need the rejuvenation, we need the regeneration of the recurring structure, we need to be able to harvest custom code, re-inject the custom code, we need that, and it is very important to identify and separate those 4 dimensions of variability that we have been discussing. The models, the mirrors of the world, where we have the data attributes, the relations, the elements, and the changes in that dimension. We would have the expanders, the templates, the skeletons, where we could have new or improved implementations of concerns, fixing of flaws, improved implementation, better frameworks or solutions for cross-cutting concerns. We would have new infrastructure or utilities, new frameworks, like I just said, new solutions for those various cross-cutting concerns, and we can have the custom code or the craftings that can improve over time. Now, it is very important that we cleanly and properly separate those 4 dimensions, those 4 fundamental dimensions of evolution in a software system. The models, the skeletons of the recurring structure, the infrastructure to deal with the cross-cutting concerns, and the custom code or craftings. Because, and that's very fundamental in modular structures, if separated well, if encapsulated well, we could have a number of versions to maintain, which is the sum of the various versions in every dimension, while we could have at our disposal the product of possible versions. Because if we separate these dimensions well, we could be able to combine without problems, without issues, all versions of every dimension with all versions of every other dimension. And that is the big promise of modularity and the big advantage of modularity. If you separate chain drivers well, if you separate variability dimensions well, then you will be able to maintain the sum of the versions in the various degrees of freedom and to enjoy or have at your disposal the multiplication of the various versions in the various degrees of freedom. And the same holds within any individual dimension. For instance, in the infrastructure dimension, you could have various versions for various parts of the infrastructure, for various subcategories of the infrastructure. And there, once again, if you separate it well, you can combine any kind of version from any dimension of variability, and you would have at your disposal always the product of available versions while only having to maintain the sum of available versions. This is absolutely crucial. This is only if you separate it well. If you do not separate it well, if you do not encapsulate it well, you have all kinds of interactions, and the effort you will need to maintain will become proportional to the product. Now, to give you a very simple example, a number of technologies and degrees of freedom, for instance, number of databases you would support, number of persistency frameworks, transaction frameworks, remoting frameworks, model view controllers, styling frameworks, access control, you immediately see that for these quite low numbers, where you have only in average 2 or 3 possible options or variants, that for these small numbers, the total sum and the total product has already a huge difference. If you take the sum of 4, 2, 2, 3, 2, and 2, it's 17. You take the product, it's 384. So you get a great variation guide if you separate it well. And suppose that you would have that in the other 3 dimensions as well. You would have 17 times 4, and then you would have 384 to the power of 4, which is a huge difference. So never underestimate this huge difference between a sum and a product. And that's the whole point of separating the dimensions of variability, of separating the degrees of freedom. As long as you separate and encapsulate it well, you will enjoy the benefits of the product, and you will only have to pay the efforts of the sum. However, if you do not separate and encapsulate it well, you will have to deal with the burden of the product. Now, the last thing we need to add here is that in a traditional multi-tier software architecture, the various classes during deployment and runtime are divided across multiple tiers. Now, until now, we always have represented a data element, a task element, as a collection of classes interconnecting with various cross-cutting concerns in a logical way. And this collection of classes belongs to a single element, a single data element, an invoice, an order, and so on. However, these classes, when after they have been coded and they are there, when they are compiled and deployed, they will be divided across the various tiers of the application. And so, for instance, if you would say, look, you have a central class which is agnostic of the technology, just representing the invoice, that's actually located in what you would call a shared layer, but it needs to be exchanged between the various layers or tiers. The same thing for the interface. But for instance, you would have a class dealing with persistency, a class interconnecting with a persistency framework, and that class would be deployed at runtime in the business logic server close to the GPA provider, even close to the database. So in that class, in this logical structure of the element, would be deployed there physically. Another class would also interact with the persistency framework would also be deployed in that part would come from the schematic representation of the element, but would there be deployed in that part of the system. A class interconnecting with a transaction framework, for instance, would also be deployed in the business server, the logic server, but a little bit different, would be connected, related to the EGB provider, and would be slightly differently deployed, would not interact directly with the database. And a class dealing, for instance, with the remote access using RMI would be deployed more at the front end or the exposed end of the business logic server. While another class dealing as a client with the RMI provider would be deployed in the presentation server. Other classes dealing with the model view controller framework or provider would also be deployed in the presentation server, but then more on the front end side of the exposed side of the presentation server. And for instance, other classes that would deal or interact with the model view model would be actually at runtime deployed within the web browser. So it's very important to see that while we represent all the various classes surrounding a central class and dealing with the various cross-cutting concerns in a symbolic way around the central class, during runtime, during deployment, they would be divided across the various tiers of a multi-tier web application. And of course, this is not only for the deployment of single elements. When you would have multiple elements, it would be clear that that would be the case as well. Every one of these functional elements, like an invoice, an order, a customer, a person, a payment, they would all have these various classes surrounding the central class, and all these various classes would be deployed across the multi-tier architecture of the multi-tier application. And from the packaging point of view, if you package it in archiving software, you need to package it based on the dependencies. So for the packaging, you would, for instance, package all the shared classes, all the classes of the shared layer with no technological dependencies in a separate archive, which has no technological dependencies. On the other end, all the classes being dependent on the persistency framework from all the various different elements or functional elements would be combined in an archive being dependent on the persistency framework and containing classes of various different elements. All the classes being dependent on the transaction framework, for instance, would be packaged together, would be combined in an archive that would be dependent on the transaction provider and that would contain classes from many different elements corresponding to the functional entities. So for instance, the transaction classes of the customer, order, invoice, person, payment, sensor, they would all be together in this archive in the logic tier. And the same, of course, is valid for the remoting classes interacting with the remoting framework, and the same is valid for the classes being dependent and dealing with connecting to the model view controller framework, and the same is also valid for the classes based on interconnecting with the model view model. Of course, if you have any remarks or any questions, you can always contact me. Thank you.